All right, so we are Friday. We made it to the end of week 3. Next week is a pretty relaxed week. I don't even think you have much work besides maybe Monday. And you've got your independent study unit, which is under the culminating, and you should have started by now. If not, you need to get on that. And then you've got your exam, which is really just a big assignment. So I have gotten questions about it. It'll be the exact same thing as your assignment, where it's just one document and you get it done. I believe I'm posting that on Tuesday or Wednesday, which gives you 2 or 3 days to work on it. You can really hunker down and get it all done in a day, and then you're free for the rest of the week. So like I've been saying, it's really home stretch here. So today we're finishing up unit 4. So you've got assignment 4, and then you've got property or probability distribution. And so that's our unit 5. And then this video is for hypergeometric distribution. So I'm just going to get over there. Okay. So what is hypergeometric distribution? So when a coach chooses a starting lineup for a game, a coach obviously has to choose a different player for each position. Similarly, when you deal cards from a standard deck, there can be no repetition. So you can't have like 2 hearts twice, right? In such situations, each selection reduces the number of items that could be selected in the next trial. So meaning when you take out that 2 of hearts, it went from a stack of 52 cards down to 51, and then it'll be down to 50 and so on. So your number of items really decreases every time. Okay, so thus the probability in these trials are dependent. So in the last unit, we looked a lot at independent events, whereas this is dependent. So hypergeometric distribution has a specific number of dependent trials having 2 possible outcomes, success or failure. The random variable is the number of successful outcomes in the specified number of trials. So the individual outcomes cannot be repeated within these trials. So again, when you're picking from a stack of cards, you can only get the 2 of hearts once. When a coach is choosing a lineup, he's only going to have, X amount of quarterbacks. I don't know much about sports. Okay, so completing your hypergeometric probability distribution. So we've got example 1. So determine the probability. I'm just looking. Yeah, okay. So this needs to be separated a bit. So determine the probability of distribution for the numbers of women on 3-person committees selected from pool of 8 men and 10 women. The selection process involves dependent events, since each person who is already chosen for the jury cannot be selected again. So the total number of ways the 3 people can be selected from the pool of 18 is, so your number of selected people is 18,3. Okay, which gives us 816. So there can be from 0 to 3 women on the committee. The men will fill the remaining positions. The probability distribution is as follows. So we fill out this table below. Okay, so we've got the number of women is X. So 0, 1, 2, and 3. So the probability of it being 0 is 10, 0, 8, 3. and then 18, 3. Whoop, that was awfully done. Which is equal to 0.0686. Okay. This guy's going to be 10 men, 1 woman. 8 and 2. 18 and 3, which gives us 0.3431. And you're going to keep going like that. So 10, 2. Mm-hmm. 10, 3. 8, 0. So the expected number of women is 0 times P of 0 plus 1 probability of 0 or of 1 plus 2 probability of 2 3 P3. So we have 0 times 0.686. I just gotta take this call. I'll take it after. Okay, plus 1. And it keeps going. 7, 1. It's equal to 1.67. Okay, so I'm clearing this. It's long. Okay, so we've got a formula that kind of helps you, so it's not as long. Okay, so our formula for dependent trials, so that's our keyword here, is P of X. So our probability of X is AX R minus X over NR. Okay, where A is the number of successful outcomes among a total of N possible outcomes, and B is the number of failures. Okay, so looking back at example 1, we could have used this formula. Okay, so our A, our number of successful outcomes is 10. Our B is the number of failures, which is 8. The number of outcomes is 18. And we've got our R, which is 3. So that's what we're looking for. So we could have just used this beautiful thing for each probability calculation. My goodness. 3 minus X over 18, 3. Okay. So I'm clearing this. So we've got example 2. So suppose you're dealt a 4-card hand from a standard deck of cards. Create a table that shows the theoretical probability distribution of how many spades are in your hand. Okay, so that'll be good there. There can be from 0 to 4 spades in your hand, right? There are 4 possible spades. The other suits can fill the remaining spots. We can use the following formula to create the probability of a 3-card hand with X spades in it. So we would do 1, 2, 3, 4. Over 52 4. Okay. I'm not going to keep writing those whole long numbers. So this one should give you 0.4388. This is 0.2135, 0.0412, and 0.0026. Okay, and the next question is asking us the possibility, or what is the expected number of spades in your hand? So we would do 0, okay, plus 1 times. Okay, so you really do that times that, and you add all of these. Bless me. 0.0412 and plus 4 times 0.0026, which is equal to 1. Okay, so I'm clearing that, and we've got one last example before we go. Okay, so we just did that. So a box contains 8 yellow, underline these guys. So 8 yellow, 4 green, 5 purple, and 3 red candies jumbled together. You randomly pour 5 candies into your hand. Create a table that shows the theoretical probability distribution of how many red candies are in your hand. Okay, so there can be from 0 to 3 red candies in your hand because there are only 3 red candies. Okay, and so our probability for success is 3. Probability for failure is 17. The number in total is 20. And our R is 5. Okay. So again, throw it into your formula. Is 0.0686. This one is 0.3431. And you keep going. This will be 1, 2, and 3. Okay. So that is it. I hope that it makes sense. Yeah, I hope you enjoy your weekend. Hopefully the weather is nice. And I'm clearing this, and that is it.